So today we're going to be doing a brief review of the kinematics chapter or unit for the AP Physics C Mechanics exam. We will not only be going over 1D kinematics, we're also going to touch upon a little bit of 2D kinematics, just so that you guys feel comfortable with kinematics as a whole. And because this is AP Physics C, right? There will be calculus involved, and not just algebra. So we will be going over some fundamental calculus concepts within the chapters. I think we'll start in about 2 minutes. My water over here. This is some pretty dense stuff, but I promise that after we do some practice problems, after we go over some definitions, it will all be much more clear. Alrighty, so I don't want to waste too much time because we have lots and lots and lots of slides to go over. But again, this is just an overview, and we will be doing additional reviews, additional topics in the future. I think the next one will probably be Newton's laws, because Newton's laws are very important. They do come up in future chapters, which is cool, in units. Alrighty, I think we'll get started. So if anyone else joins, I will let them in. Hopefully I can see the waiting room. Let me just double check. Yeah, I think they can see. All right, okay, let's just get started. All right, so this is our first content-based office hours. Our last office hours, I basically went over the entirety of the exam, what's going to be on it, what's going to be in the course, things like that, what units you'll be looking at, things like that. So today we're going to be doing a concise, hopefully it'll be helpful, review of what is kinematics. All right, let's get started. Again, I'm just going to share this one more time. Please make sure you are following Haivel's 3 social media pages. They are definitely really helpful in finding like certain information stuff. So definitely make sure you've added Haivel on Twitter, Instagram, as well as YouTube. All right, I'm going to go on to the next slide. All right, so today's agenda, as you can see, we're going to hit a lot of different things. So we're going to start with an overview. We're going to start with position displacement. Those are three very important phrases, definitions. We are going to go over those. Speed and velocity, we're going to get deeper and deeper. Then we're going to go into acceleration, right? We're getting deeper and deeper. The big five, we're going to talk about the big 5 equations. Graphs, because that's a whole other ballpark, a whole other ball game, I guess you could say. I'm going to kind of go over the different graphs, because using these terms, so we're going to kind of go in order. Then we're going to go over free fall. Then we're finally going to go over projectile motion. All right, I'm super excited. All right, so let's do an overview. So we're going to explore dynamics and movement. We're going to explore the necessary equations, as you can see, the big 5, right? Big 4, I should say. There is actually a 5th equation, but on the AP Physics exam, you will mainly just be given these 4, and it's good to memorize them, so it makes your life easier because you can get through the questions faster. Yeah, big 4, sometimes big 5, so we're going to call them big 4 for now. We're going to be asking and answering why objects move the way they do using both algebra and calculus. We're going to figure out how to calculate objects' speed, distances, and the rate of change of speed. Woo. All right, let's get started. All right, let's quickly go over position, distance, and displacement. And I'm going to check the waiting room one last time before I really get into it. I want to, hopefully, can I check the waiting room? So I think, just give me one moment. Technical difficulties. All right, we're gonna share screen one last time. Okay, let's get started. So I'm gonna read through these, and then we're gonna talk a little bit about them. So position, distance, displacement. They are, I know these seem like similar things, but they are slightly different. So position is opposite to the coordinate axis system, right? Position just kind of tells us where the object is, right? Distance is a scalar, meaning it's just, right, a number in units. It is a scalar that represents the total amount traveled by an object. And let's compare that with displacement. Displacement is an object's change in position. All right, so I'm going to talk a little bit. I do have another slide. I don't want to go too much. Yeah, I definitely like this visual. So displacement in its most simplest terms is the change in position, right? Displacement doesn't care about the path it took, right? We don't care, like displacement doesn't care if you start from this point, and let me just get my pointer for a second. Displacement doesn't care if the object moves this way, then moves back, then moves this way, and this way, this way. Maybe it goes around in a circle a couple times. Maybe it goes back for a second. Maybe it zooms forward and then stops here. Displacement doesn't care about any of that. Displacement only cares about your initial position and your final position. However, distance, right, just like its definition, right, it represents the total amount, right? This distance cares about that stuff. Distance cares whether you go forward, backwards, right? All of it's just added up. Displacement, really important, only cares about the initial and the final, right? Change in position. Okay, so I believe I do have a practice problem. All right, so in a track and field event, an athlete runs exactly once around an oval track. A total distance, so I'm just gonna underline some keywords. Remember, position, distance, displacement are three different things. Particularly, I also want to emphasize distance and displacement are two very different things. So total distance of 400 meters. Find the runner's displacement. All right, so let's figure this one out. So I would first draw pictures. If anyone's unfamiliar with what a track and field kind of oval, that's a really bad oval. That's a good oval. All right, so so that is the picture, right? I'm gonna start the runner's initial point. That is where the runner starts. Right, so the runner is gonna run, right? And this is the circumference, right? And this oval is obviously 400 meters because that is like the distance. That is what the runner has. That's the path the runner took, right? But right, it's not asking for distance. It gave us a distance. We have to find displacement. Remember, displacement does not care about the path you take. It doesn't really care about that stuff. Remember, displacement is the change in position. So final position minus initial position. It doesn't care about like the stuff in the middle. In this case, you can kind of think about it. I'll give you a couple seconds to kind of think about it. And don't overthink it, right? So exactly once, right? Pretend like you're the runner, right? You're running, right? Where do you end up, right? You go back to your starting position, which means the initial position and the final position are the same, which means even though the runner ran, right, 400 meters, right, runner went all around the oval, right, the displacement is 0, which is kind of cool. So that is the displacement. So yeah, the distance is 400 meters. I know it's weird to think, right? The runner the runner ran around, right? Shouldn't that, count for something, right? So that's accounted in distance, but not displacement. The runner displacement is 0. So I think it's pretty interesting. Okay, so let me erase that. So let me show the answer. Hopefully it comes in. Yep, there we go. Total distance we were given was 400 meters. So displacement will be 0. Cool. All right, so next up we've got speed and velocity. So again, we're kind of growing on our topics, right? So we're taking what we just talked about and now we're expanding a little bit. So next up we got speed and velocity. So we're first going to talk about average speed. So average speed, just put it simply is total distance divided by time. Time required to cover that distance, I should say. Speed is a scalar. So the example that I like to give for speed is like the speedometer, right? The little like thing when you're driving a car, right? Tells you by like bounces between the numbers depending on how fast you're going, right? The speedometer, I think that's how you pronounce it. Right? It doesn't care what direction the car is moving. I know some cars, they like on the top of it, they have like, oh, you're moving northwest or like southeast or something like that. But for most cars, the speedometer, it doesn't care what the direction is, right? That's a scalar, right? We'll talk about vector in a second, but yeah, scalar means we don't care about direction, we just care about the number and the unit. So for example, like 55 miles per hour, 32 miles per hour, 32 feet per second, I don't know, things like that. That would be average speed. Then we've got average velocity, and this is important to note. So whereas average speed is total distance, so I'm just gonna write that down because I think that's a really important distinction. Whereas average speed is distance over time. I'll just do D for now, or I'll do, we'll do this. Oops, well, this is kind of hard to write with a pen. Right, so whereas average speed is distance, right, total distance, right, which we just defined before, whereas average speed is total distance over total time, average velocity is displacement over time, which I think is pretty interesting. I'll just write, so you write the whole word, right, which is cool. Oops, why can't I? Okay, there we go. Alrighty, so that is the kind of definition of average velocity. Velocity is a vector, right? Because vector is not only, what do you call it? It's not only the number, it also will have a direction. All right, let's see if there is anything else that I wanted to mention. I think I have more. I don't want to give too much. One second, let me erase this for a second. I'll just click clear. I believe I had another slide. Yes, this is exactly what I wanted. I'm so glad that I included this. So sometimes it gets a little bit confusing, right? Which one is which, right? So this is a really easy to kind of digest. Obviously, we don't really care too much about mass and weight right now. Right now, we just care about kinematics. It's all about movement and stuff. So we're just going to take a look at distance, speed, displacement, velocity, acceleration. And we'll define acceleration in a second. But scalar, right, only has magnitude, right? So distance, that would be example of distance. Speed, right? Whereas vectors, right, have magnitude and direction. So displacement, right? Velocity, acceleration, things like that. Alrighty. Of course, I know sometimes velocity is expressed without a unit, and sometimes, and how you know when to do that is if the question asks, give me the magnitude of the velocity. If the question is phrased like that, right, then you don't need to direct. If it says only give us the magnitude, then sometimes you might see someone might just write V equals 5 meters per second, right? That's okay. However, right, and usually that's how most questions, right, is care about the magnitude, but just remember vector is magnitude and direction. So pretty important. Okay, so now let's take a look at more of the calculus side of it. All right, we're gonna move kind of away from algebra for a second. So we've been talking a lot about averages, right? So for example, I'm gonna go back to the car speedometer. I'm just gonna say speedometer. Right, the car speedometer, I'm pretty sure I'm pronouncing that wrong, but it's okay. It tells you not the average speed, not the average velocity, but it tells you the instantaneous speed, right? Which is interesting, which is different, right? So instantaneous speed tells you the speed at that exact moment. right? So average speed and average velocity, we just defined it, right? It's either total distance over total time or displacement over time. Instantaneous speed is right now. What speed am I going right now? This moment, this second. Not I only care about total time, whatever. No, it's right now. What am I going at? Am I going 3 meters per second? And then 1 second later, I'm going 4 meters per second, right? So instantaneous speed is right now. And that's where calculus comes in, right? For instantaneous speed, instantaneous velocity, we need calculus. So that's where the distinction is kind of made. Okay, so let's go to more of the calculus side of it. So for here, right? So here is basically this really neat chart down here. When to differentiate, when to integrate. So velocity, right? So instead of saying velocity is the change in, right, delta x, right? Instead of just saying that, right? We basically turned the delta into a d for derivative, right? Because we're kind of working with deltas, right? Instantaneously or infinitely, right? The change in t, I should say. The change in t is so infinitely small because we're trying to get like right now, right? So we're trying to get it so change in t is almost, right, as infinitely small as we can get. So that, yeah, that's where calculus comes in. We've swapped the delta for a d, right, to get derivative, right? Derivative is slope. We'll talk more about slope and stuff in the graph section, but right now, just this is kind of the cycle, I guess you can say, that you should probably remember. So again, to get velocity, you have to differentiate your x. I know sometimes they put s and x, so just differentiate between like position, this is displacement. Sometimes I know displacement is usually given an s. Doesn't really matter what variable you use as long as you know what you're using. I just use x, x, b, and a. Those are the 3 variables I use. I don't really use s too often, but whatever kind of floats your boat. So however, let's go back to our calculus concepts for a second, right? So if v is equal to, right, dx or dt, right, what's the opposite of differentiating, right? In taking integral, right? Taking integral is the inverse of taking a derivative. So given this, right, v equals dx over dt, right, x will now equal, right, the integral of v, right? So again, we can go back to our chart for a second. So going from distance to velocity, you differentiate, right? And then going from velocity to distance, you're integrating. So let's do a quick example. All right, oh, this one's a doozy. All right, so an object's position, x, in meters, follows the equation x equals sine t, where t is the time in seconds since the object began moving. How fast is the object moving at t equals pi over 2 seconds? Okay, this is a lot of information. I'm going to be brutally honest here. That was a lot. Let's label. Let's go nice and slow so they don't get confused. Let's go nice and slow. The question, so how fast? What is it asking? What is it actually asking? What variable are we looking for? How fast? That's velocity, right? So we're looking for v. At t, so v, at symbol, v at t equals, oops, that is a weird equal sign. T equals pi over 2. Okay. So let's go back to our definitions for a second. We're given, right? We're given the position, right? X. We're given that position formula, right? Because that's what the object is following. So if you guys remember, I'll give you a couple seconds to recall what the last slide said. Velocity, right, is the, let me write this down really quickly so that I can see. We take the derivative of the position to get the velocity. Right, so this is the equation, right? So and then that's how you forget, like, right? Because sometimes it gets confusing, you don't want to memorize it. I just want to really quickly just draw like a parallel between the two, right? So if you forget, just remember that, oops, that looks like a Y actually. Let me turn that into a V. So yeah, average. I'm going to take the average, for example, the average formula. So again, average velocity, right? Let me put this over here for a second. Average velocity is equal to, right, displacement over time, total time, I should say. And let's see, we have, oops, let me, hold on, the waiting room. I forgot to check the waiting room. Alrighty, there we go. Oops, hello. Hi. All right, thank you so much for joining. Oops, here, I can actually start with a question really quickly. Thank you for joining. Oops, let me just put this over here. I haven't been checking the waiting room this entire time. I am multitasking here. All right, so really quickly, I can just go over this question one more time. Let's pull this up.
Right. Sorry for being so late. I totally lost track of time, one, and didn't check my Slack, two, and also misread the time for this stream. I read 6 Eastern as, Pacific, and yeah, that was great.
No worries, and no worries at all. No worries at all. I'm also, that just reminded me, I need to post the link in the thing. Yeah, let me just put that right there. No worries. Oops. Hold on. I am multitasking. I have like Slack open. I have Zoom open.
Right. Yeah.
Let me just put this. Oops. Okay. Let me just go back. Okay, so basically, I've just been doing a bunch of practice problems and definitions.
Right.
So I'll just re-explain this one really quickly. Sorry. So
I did want to ask actually, just like about physics C in general, right?
Yeah.
Like I personally haven't started learning any proper physics C content besides like basic particle motion and things, or like kinematics, I guess, because that's what we also cover, one in physics 1 and also calculus AB, which I did last year. I didn't do physics 1 last year. I did calculus AB last year. So yeah, like I don't know what to cover right now, and I'm trying to look in the CED and everything, and I guess like it's just like figuring out pacing and everything is like the biggest challenge,
For sure. Oh yeah. Or are you let me see. So yeah, definitely. This is definitely. I did not self-study this course. Because it's very dense. Let me just pull up the different units really quickly. Because I think it's pretty important to go with kind of in order. Yeah, definitely go in order when you're.
Right.
If you're using a book, definitely go in order. Do not skip around. I think.
Yeah. Right. One thing builds off another, and yeah, it's just like calculus.
Definitely. Yeah. So yeah, since you already have some calculus background, that is so helpful. I actually went into physics C mechanics with no calculus background. Like I was taking calculus while taking. I mean, it's manageable, but not the easiest.
Not advisable. Yeah, no, I totally understand. I personally had a lot of time to like focus on calc last year, and I'm absolutely loving calculus. Like it's my favorite school subject, like by far, that I've like completed. So
yeah. That's amazing. That's awesome. Yeah. That is awesome. I cannot say the same. Calculus, even though I love physics, calculus is a whole other like ball game for me. But yeah, they're similar, similar and different, very different at the same time.
Yeah, like personally, what I'm thinking is happening is like people who are more like humanities oriented tend to think more realistically, right, and less mathematically, right, and that's why they would like physics over calculus.
Yep, you got it. Yeah, that's exactly. I do not like the theoretical stuff. Like I want to like reality. I want to know the ball's moving, the car's driving, like things like that. That's quick.
Yeah, I'm the opposite.
Once you ask me like curves, it's like, what? Where did that come from?
Yeah, no, I totally get that.
For sure. Yeah, because I'm currently taking Calc BC because I took Calc AB last year while I was taking Physics C mechanics. Yeah, like I know like they're probably kind of similar with physics and calc, but I will say physics was something I enjoyed a lot more. Calc is it's hard. It is hard.
Yeah, no, I get that.
For sure. But yeah, going back to the units. So definitely make sure you are solid on each unit before moving on to the next. So yeah, right now we're just doing a kinematics review. So I'll do some practice problems right now is a practice question. So make sure you're solid on kinematics, both 1D and 2D, and then do some practice problems with those. And then once you feel good with that, then move on to the next unit, which is Newton's laws of motion. I personally think you should be spending at least like, let's see, so the exam's like in May, right? So, and there are only, so for this exam, you have 7 units. I would spend at least like 2 weeks or even 3 weeks, even a month if you can, on each unit. Just make sure you fully understand it. Because, for example, if you just speed through unit 1 or speed through unit 3, you're gonna get kind of confused with like unit 5, which is rotation. And basically everything you've seen from unit 1 kind of just appears again in unit 5, but in like a different way. So I would say make sure you like don't speed through it. This is not probably not the course you would want to speed through, because especially unit 3, I will say for me personally, and for what a lot of my classmates said, unit 3 was actually like one of the hardest like to understand, because that one actually is pretty theoretical.
Yeah.
Work, energy, and power. Whew.
Right. Yeah. Yeah. That is like work, energy, power, and things. Yeah. Yeah. That sounds interesting. Yeah. So to be quite honest, like what I've been feeling like I'm doing is just jumping around a lot, like the exact opposite, right? Because at this point, our school course is totally stuck in like one-dimensional, two-dimensional kinematics, and like I guess that would be okay, but like we still have a lot to cover in AP Physics 1, right? Like we don't just have like 7 units; we have a lot more, right?
Yeah.
We just barely finished up like one-dimensional kinematics like a week ago, which is great case.
That's okay.
We started mid-August, so.
Oh, August. Oh, wow.
Yeah.
Ooh. Yeah, definitely. So wait, is that for the AP Physics 1 course, or is that for the AP Physics C Mechanics? Yeah,
that's
I know
for AP Physics 1.
Well.
My school doesn't offer C Mechanics.
Got it. Cool. Yeah, so I would say, yeah, definitely, it's definitely doable. I can do mechanics instead of 1, because all the difference is just calculus to algebra. Let's see.
Like, to be honest, like I'm using like calculus concepts to like understand things like the kinematic equations or something, right? Because like velocity is the derivative of like speed, and like velocity, like the function of time, is literally just differentiate that kinematic equation for displacement, and that's all it is, right? So
exactly. It's like average versus like instantaneous. Actually, hold on, I have a cute slide about that. Oh, not this one. Ta-da! I created a cute little comparison of when you use algebra and when you use calculus. Because that is a question usually people ask.
To be quite honest, like calculus for me is like what I would prefer. I personally would prefer calculus over algebra, because like calculus, even though I've had like 1 year of experience with it, like I've taken a whole AP course in it, right? So I really do understand these like concepts, as opposed to just algebra, where I've been like just going through our like school units and barely doing anything in our finals. So.
Right. Yeah. Definitely. I think all up to like preference. Like me personally, if I could choose, algebra all the way, because it's
No, I guess that makes sense.
Yeah, that's okay. Yeah, that's actually pretty cool. The fact that you like calculus and you're good at it, like that'll make your life like 10 times easier. Like future calculus courses and stuff. So I wish I could like enjoy calculus. Like sometimes I'll just like study and be like, I wish I could enjoy this.
That's me with history.
I can't find it.
Yeah, I cannot manage history. Like history is the slowest thing for me. Yeah.
For sure. Let's see. Right. Yeah. Any other questions? Sorry, I don't know if I half answer your question, like going in order.
That's okay.
Yeah. Give me other questions.
Yeah. So again, like 2 weeks to a month for like each unit. So maybe like a happy medium would be like 3 weeks. I can go and plan that out. If I need to take more time, then I have a bit of like wiggle room, I guess. Yeah. It's just like I've never planned out like a whole curriculum for myself. I don't even know where to start. Like, just as like someone who's like self-studied, like what would you advise doing first?
That's a good question. So me personally, I've actually never self-studied an AP course or AP exams before, so I'm probably not the best person to ask, but I'm just
Oh, right. Okay, I thought you did self-study, see.
No. I've never self-studied an exam. Yeah, that's okay. So yeah, even if I give an advice, it's probably not the best advice because I've never done it, so take my advice with a grain of salt. But I would say probably buy like one of those like prep books. They probably go pretty in depth. Yeah, probably. Like Barron's, I think. I have the Barron's AP Calc book actually. I was like struggling. I was like, I don't get this. I need more practice. So Barron's goes pretty in depth. Yeah, definitely get one of those. Also, sometimes they don't go too much in depth, or like they're really wordy and like they just don't get to the point. So I do have the Princeton Review for AP Physics C, and like it's pretty wordy, I will say. So I would say for certain concepts, it's just like, I don't get it. Definitely go to YouTube. Like watching videos has helped me a lot. I think, let me see, flipping physics. I mean,
Oh, right. No, I've compiled like a whole list of like online resources and things. I can maybe share it with you actually if you would like me to.
Sure, yeah, that would be awesome.
Yeah, I have like a whole Notion page. I've just dumped everything in there.
Fancy, nice. Speaking of Notion pages, I
use Notion for like everything now.
yeah, me too. Oh my God, Notion is a lifesaver. It's like basically like Google Docs, but like fancier. Like you can like turn your notes
it's great
into like a website almost. Like it looks so cool. I love Notion.
Yeah.
I also, let me see, hold on, let me pull this up really quickly.
Okay,
I do also, yeah. Sorry.
Oh,
no, go ahead, you're fine.
Hopefully you can see that.
Oh yes, I see it.
Yeah. Yeah, I've just like dumped all of these like physics things that I found in here just today afternoon, really. So
oh my gosh,
it's very
awesome. Oh, I love.
Yeah, it's very incomplete, but.
Ooh, nice. Yeah, this is perfect. I'll definitely share, or you can share in the channel just so this is.
Yeah, I mean, I can stick this in the channel actually.
Oh, I see that. Hold on. What's the last? Hey, is that the fileable office hours?
Yes. Yeah, I mean, all of that's there, and I'm planning to just add to it as I go along. Oh, this link needs to go there too.
That is perfect. That's awesome. Let's see. Yeah, they're all. Yeah, that's awesome. All right, yeah, it looks like you're pretty prepared. So now it's just like a matter of like I know for calc at least, I also think some of this like on Google Docs where I had all my resources. But then like I noticed like as like the date like creeps closer to like the AP exam day, like I would just like not open some of the links. So I was just like I'm just kind of lazy. So just make sure when you like these down, make sure like I don't know, you kind of pace yourself. Make sure I'm checking each of these links and actually opening them. Maybe I'm just lazy. I just didn't do it, but that's awesome.
Right. So I also found this like entire textbook or something online, which is interesting. Yeah. So I think I'll also use that.
For free. That is amazing. Yeah, definitely. So yeah, just make sure like it has like all the same units. Sometimes I have some textbooks they like it's not like aligned, I guess, with the AP exams, so you have to do like outside. But that's awesome.
But still good for like practice and everything.
Good. That's awesome. Free stuff. We love free stuff. Oh, great. Oh, great. We'll check the time. Oh, yeah. Okay. So let me, all right. So I'm going to quickly, oh, wait a lot. Okay. So I'm just going to go back. So yeah, just jump in if you have any other questions. Okay. So I can just do this one really quickly. So this, yeah, before we came, I was just like talking about, hold on. I was just talking about, right, like the calculus stuff, so the instantaneous velocity, going back and forth, integrating, differentiating. Pretty simple stuff.
That Scalar one, that would be 0, right? Because you plug in pi over 2 into cosine, and then yeah, you just get 0.
Yes, you got it. Perfect. So I'm just gonna do the problems again since I was watching the replay. I'll just do it really quickly. So, so how fast? Again, that's keyword for velocity. Oops. Let me just put a little at symbol.
So
I'll just write it down. Yeah, go ahead.
Yeah. So when they ask how fast, right? Like, does that have to be speed or?
Yeah. So that would be speed. Yeah. So if it asks like, what is the rate of change of the speed, that would be right acceleration. But yeah, if it's how fast, speed or velocity.
That would be right. Okay. Yeah. So in what instances would you have to answer with like velocity, like the rate of change of like displacement, obviously, but like they're not really going to say it. They're just going to say velocity.
Yeah. So if it said, so going from position to acceleration is very easy. You just differentiate, right? So it would say something along the lines of like, what is the rate of change of the speed of the object? You would probably see something like that. Like, yeah, there's probably no like easy way to say, or you can say like how fast is the object accelerating.
Oh.
There's really no
how
easy.
How fast is the object accelerating? Wouldn't that just be like the derivative of acceleration, which is like?
Oh yeah, no, I meant what is acceleration? Yeah, there's really no easy way to say like that acceleration. Yeah, so I would say, yeah, from what I've seen, from what I remember, it would always say like things like what is the rate of change of the speed? Because then it kind of takes, like, again, it's like they're trying to test to make sure you know the acceleration is a change in velocity, which I'll go over in the next slide or future slide. Yeah, that one's it's a weird one. You just
so it's basically just like
casually.
So it's basically just like how like a calc problem would be worded, right? It's just like they would use the same wording, like they wouldn't use anything fancy, I guess. So.
Yeah, physics sometimes they kind of trick you with the wording. Sort of always fun. All right, let me just finish up the writing. So if anyone's watching the replay, you kind of know what to do. T derivative of sine is cosine of t, so some calculus knowledge. And then from here, we can just plug pi over 2 straight in. Cosine of pi over 2 is 0. Wait a second, sorry.
All right,
but like, an interesting one. Yes.
Yeah, but like cosine of t wouldn't be equal to 0. That's a bit strange.
No, cosine of pi over 2. Sorry. Cosine plug in. I skipped a step. Supposed to be cosine of pi over 2.
Right, yeah.
There we go. Equals 0. Ta-da. Where's that? Equals. Sideways.
I'm not sure,
there
but
we
like,
go.
I think they would just mark that as like straight up wrong in like a calculus test. So I don't know if they do the same in physics.
Yeah. So I'm not being too technical right now, but technically it should be cosine of pi over 2 equals 0.
Yeah, but that makes sense. Yeah, sorry about that.
Yeah, no worries. All right. So that is the answer. That's kind of interesting. The speed is 0. Box it in as well. Okay, cool. So that is that one. So again, this one, the only knowledge you needed was just knowing the derivative of sine. That's all you really need to know. Like outside background knowledge. All right, so let's move on. Hopefully it should pop. Yep, there it is with the answer. Okay. Acceleration. So I'm just going to quickly just define it. So average, so I'm just going to talk about the average for a second. So average average acceleration is equal to the change in velocity over time. I'm just going to write that over here, just so it's easier to see. So it's a change in delta V over delta t, or just time. Time too. Make a little. Oh, actually, I'm going to do a lowercase a, so we can be super technical about it. And for anything with average, you always put like a little line. All right, there you go. So I forgot to add that. So that is for average acceleration. So for that, you just use algebra to solve. Let me put this over here for a second. And because velocity is a vector, acceleration is also a vector. So let's now look at the calculus side of it, right? So let's say we wanted to find the instantaneous acceleration, meaning the acceleration right now, this current moment. So then you would have to use acceleration. So basically, you can kind of see a similarity between instantaneous and average, right? So we just swap the delta for a d, right, to represent derivative. So if you forget, let's say you forget, like, a is equal to, is it dx or dv? Just remember the average definition. Swap the deltas for d's, and there you go. You've got your derivative stuff, calculus stuff. So again, velocity is the derivative of position. So that means acceleration is the second derivative of position, which is kind of cool. We're kind of combining concepts here. And then let's just do really quickly, if acceleration is equal to dv over dt, we know that velocity then is the integral of acceleration. So we just swap it around. That definition of the integral, definition of the derivative. These are kind of our definitions. Let me just rewrite these. So I kind of couldn't find the integral symbol, but I can just really quickly label these. Let me label A is equal to dv. There we go. All right, cool. And all right, so I'll leave that screen up for yes. Go ahead.
Just a quick question about the notation for average, things. Is it just that little line on top of the variable for it, or the symbolic representation?
Yes. So just because a big question for physics is like this, how do we distinguish between like instantaneous and average? So usually it depends on the context, because sometimes oversimplification can actually get even more confusing. So usually I know some books, they just write like average acceleration as normal A. But if I guess like the technical like notation, technically, having the little bar above it, and also I think like statistics, too, the same thing in statistics, like they want to find the average something and you just put a line over it. So if we're getting like super technical about it, A with the bar above it is average acceleration, whereas just normal A is your instantaneous acceleration. I know sometimes it gets confusing. Sometimes in like, what do you call it? Like in the beginning of a unit, teachers will just like, or textbooks will just have the normal A, just represent average acceleration. That's where it gets confused. But yeah, it gets confusing. So however, if we're being like super technical about it, this is instantaneous, like right now. This is the acceleration right now. Whereas this is the average. And then if we only, I guess more for comparison purposes, like if we are only dealing with average acceleration, like the problem never mentions instantaneous, then I guess you can just put an A. It gets kind of tedious to keep putting the bar over it. But if we're talking like definition-wise, this is the correct way to kind of distinguish between the two. Because otherwise, how do we know which one's average? How do we know which one's instantaneous? So for definition purposes, we put the bar over and don't put the bar over instantaneous. But I guess for practical purposes, if you're just answering questions like what is the acceleration given, your change in velocity, change in time, I guess you could just put that.
Right. Okay. Thank you.
Yeah. No problem. Great questions. Oops, how do I quickly clear this? Okay. Hopefully, did I put the slide in? Yes, I put the slide in. Okay. This is my favorite graph. And I already had this on a couple slides, but this one is just much more clear with the arrows. I always memorize this. I just remember, sometimes it's a little bit tedious. It takes kind of a long, especially if you're doing this super long problems, again with physics, C mechanics, FRQs. They're pretty long. They're usually pretty long. So let's say you don't have time to, what is the definition of velocity? What's the definition of acceleration? It can get kind of tedious, but sometimes I just memorize this. So I want to go from displacement from X to V, right? I just differentiate, go from V to A, differentiate. When you're going back, I sometimes think of it like I'm getting more and more complex. So this is like a more casual way of just remembering it. So right, so I'm going from position or displacement, whatever you want to call it, X, I'll just call that a variable. If I want to get more complex, I want to find velocity now, I just differentiate. If I want to get more simpler, I integrate. That's one way of remembering it, or just memorize this graphic, whatever helps. Or if you don't want to memorize it and you want to know exactly what you're doing, right, just remember the definitions of the average stuff, swap the deltas to the d's, to the derivative, and you'll have your answer. And then to get the integral, you just play around with it, right, the definition of integral. So things like that. But yeah, this is a very important graphic to remember what you do for which one. And I think I have a next. Oh no, not quite. Okay, this is not related to the exam whatsoever. I thought it was kind of funny. So right, going with the right. So if let's call it differentiating, right? If you keep going, I thought this was a joke, and my physics teacher taught us this. I thought it was a joke when she brought it up, but it's not a joke. Snack, crackle, pop. That was a real thing. So I found some cool graphs. So I will talk. I have a whole slide for graphs. I explain what they are, but if you keep differentiating, right? So I go from position to velocity to acceleration. So yeah, jerk would be like, right, the change in, or the rate of change of the acceleration. Right? We're just getting more and more. Again, not practical at all, but still kind of fun. So you differentiate acceleration, you get jerk. You accelerate jerk, you get snap. You differentiate snap, you get crackle. Differentiate crackle, you get pop. Jerk, I mean, I know maybe some problems they actually jerk. It's not really too uncommon, but snap, crackle, pop. I think that's just for humorous purposes. They are real. I did have to look them up. I thought I was being lied to, but I guess they exist and they're funny. Not practical again. Yeah, not practical. Not practical at all. I don't know why you would ever need to know pops, for example. How is that useful? I don't know. Again, for the practical stuff, not practical at all. Position, velocity, acceleration, jerk. I would cap it there. But just for fun, snap, crackle, pop does have a place in physics, C mechanics. All right. All right, oh, let's do a practice problem. Okay, so this one is a doozy. So I'm going to read it off, and then we will kind of go through it. I do have the answer on the next slide, but I just want to make sure anyone who's watching the replay can pause here to read a question and answer it. Okay, so I'm going to read it really quickly, read it nice and slow, because for me personally, whenever I do physics problems, right, you'll mainly see lots of numbers, lots of words, lots of key words, lots of key phrases. So you want to be looking out for those things. Okay, so let's read next one. An object is moving along the x-axis with an acceleration. Here we got a formula. Ooh, so already in the back of your mind, you should be thinking, all right, I've been given like, you know, an equation for acceleration, which probably means I'm probably going to be working around with it, you know, usually maybe to find velocity, maybe to find displacement. That's what our brain should be doing, or position, I should say. All right, at time t naught, that's what the special name, or initial time, 0, the object is at x equals 6 meters, and it is moving at 2 meters per second. So those are our initial givens. How fast, and let me just underline some key words here. How fast will object be traveling at time t equals 4 seconds? And oh, we got another one. Where will the object be at time t equals 4 seconds? So I'm going to pause for 4 seconds just so we can, 4 seconds, just to digest what's going on. I'm letting you know right now what the two things we are looking for are velocity and position. So the two things we're looking for. All right, let's jump right into it. So I think I have the answer on the next slide. So I'll just solve it. Let's see, let me put it over here. I do have the answer on the next slide. That's okay. I will just solve it right here on this kind of small, but it's fine. I want to make sure that everyone's kind of on the same page. Okay, so if you remember from the graphics, right, we need to go from acceleration to velocity, right? That's the first thing you should do. How fast, right? Let's do velocity first. That's the easiest jump. So if you remember from the definition, right, to go from acceleration to velocity, right, to get less complex, I guess you could say, you have to integrate. So we're integrate acceleration. So this is where our calculus comes in. If you know your calculus stuff, this is easy peasy. But if not, that's okay. We're just gonna do it nice and slow. You know, I'm just gonna put here. So V is equal to integral of a t. Very super formal about this. A t. All right. Okay. All right, we put our little equation in. Okay. And then we're going to integrate that. So some basic. Can I hold on? Move it over. Yes, we can. Oh, that's awesome. Okay. And then that is equal to 2 t squared that you raise the power, and you divide that to the number. Okay. 17 plus c. Don't forget your constant. Okay. So we're not done. So this is our new. Let me just really quickly hold on. I always have some of that habit of just like putting random stuff everywhere. Okay, so that is our velocity function. So we had our acceleration function. Now we have our new velocity function, but this is not complete. We have a constant, and we can actually solve for this constant because we were given something. So here, I'm going to highlight some different color for a second. I'm highlighting it in pink. We were given some information from here to here, some givens. So we were given that at time naught, or time equals 0, the object is at 6 meters. However, the one we are looking for right now, right, we're working with a velocity function. We don't really care about position. We care about velocity. Velocity function, we need velocity. So we are just given something. So time equals 0 is 2 meters. We can plug that in to find our c. So just to really quickly, we're kind of running low on time. So I'm just going to really quickly just tell you the c is 2. Then I'll just verbally explain, because on the next slide you have the answers, and if you're watching the replay, you can just pause it there. You're gonna now plug 2 into c, right? So now we have a complete velocity function. And then you're just gonna plug 4 in, right? So v of 4, plug 4 every time you see a t. You should get your answer. For the position, just remember, right? So we're going from velocity to position, right? We're getting less complex. I know that's like the most super casual way of explaining it, but that's kind of how my brain kind of phrase things. So going from velocity to position, we are getting less complex, so we're integrating. So we just integrate, so x is equal to the integral of the velocity function. We're going to integrate that, and then you will also end up with a c. You use your given, right? We're given that when t is 0, x is 6. So every time t is you put in a 0, and you should get that c is equal to 6 again. You get your official position function, and you plug in 4, and you should get your answer. So I'm gonna go to the next slide. Ta-da! So yeah, your answer. I did the work, basically what I just explained, just written out. If you want to pause the video now, you can, just to see how I did it. But again, it's just calculus. So I just want to make sure to emphasize how you do a problem, especially if you get it wrong. You want to make sure you understand what background information did I need to know to solve this problem successfully. Obviously, calculus is one of them, but for physics-wise, the concept you really need to make sure you knew was the relationships between position, velocity, and acceleration. That's the only background information you need to know. Everything else is just calculus, which is cool. All right, let's move on.
Oh, sorry about that.
Yeah.
Sorry about
go ahead.
there. But I just had a quick question about calculator use for that one.
Calculator.
So like it's just this like rather large polynomial. Like it's not too complex, but like because it's just like physics and they're trying to like teach you physics concepts, like would they allow the use of a calculator for that one, or like I'm not quite sure how that works.
Sure. Oh, calculator to solve or to graph it?
Oh, sorry. Just to do those like numerical calculations at the end.
Yeah.
I guess.
Oh yeah, definitely. I had to use a calculator for that. Yeah, you would. This would be a problem that you would definitely, because these are not friendly numbers. Like if it was like whole numbers, like yeah, like 3. Maybe yes. If t was a little smaller, like if it wasn't 4, maybe it was like 2, and it was like 3t cubed plus 2t squared plus maybe 2t plus 6. That maybe might not get a calculator because they're pretty easy. Like just if time was 2, and you got whole numbers, maybe that would be a non-calculator question. But because yeah, you got some fractions, it's a big like 4 cubed. Ooh, that's a doozy. You probably would get a calculator. I cannot promise that, but however, let me see. It's like 4 cubed. Yeah, it is. I mean, it's not. Yeah, it would be like times 2. Yeah, I guess a little bit tedious. So, oh yeah, for this one, actually, yeah, I just rounded to the nearest 10th as well. I think, yeah, if you do it, it's actually 6 repeating. I do remember doing it for my calculator. Let's see. Yeah, this would probably be a calculator question. I don't see why this would be a non-calculator. That would be cruel. But if it was a non-calculator, they would definitely pick little nicer numbers, hopefully. So that's kind of my 2 cents. But yeah, I would say for this one, the main, I guess, like emphasis would be on the calculus concept. If you know how to integrate it, I'm pretty sure that like maybe for multiple choice question, it might be like, which of these is like the correct position, I don't know, formula, position function. And then it would have like maybe this as one, this would be the correct answer, obviously, and then like maybe other ones where it's like, it's a 2/3, like 3/2, like slight changes. So you would have to make sure you just use a calculus concept.
Right. Excuse me. On the AP Physics test as a whole, are we allowed a graphing calculator or just like a normal like scientific calculator?
I'm pretty sure, yeah, graphing calculator. Let me just double check on that because I use the graphing calculator. Yep, you are allowed to use a 4-function scientific or graphing calculator. So yes, my advice: use a graphing calculator, especially if it's like a graphing question and you have a scientific calculator. That might be a problem. So yeah, definitely bring a graphing calculator to a test.
Right. Thank you.
Yeah, no problem. That's a good question. All right. Oops. Let me move that back up. Okay, cool. Let me still check on time. Oh yeah, we're good. We're good. Okay. All right, big 5. So I'm just gonna go through super quickly. So I know some people call it the big 4, some people call it the big 5. It kind of just depends on which 4 equation. I mean, usually they always pick numbers 2 and number 5. However, so my advice would be you should probably memorize these equations. However, it's important to note that these equations will be on the AP Physics C Mechanics what do you call it, equation list that you, or reference sheet, I guess, that you get for every test. So I just technically don't need to memorize them, but it just makes your calculations this much quicker when you have them memorized. However, it's really, really, really important to emphasize this because obviously at the start of your kinematics unit, the questions will be simple and the condition will always apply. But sometimes in like future problems where acceleration is not constant, you can no longer use this equation. So really, really important. These 5 equations, so the big 5, I guess, or the big 4, depending on if you want to include the big 5 number 1. That one's simple. It's really important that these equations only work when acceleration is constant. Like, if the acceleration keeps changing, right? Because we've kind of set a as one value, right? One number. Because if a keeps changing, right, we can't just keep changing the a because then the entire equations change. So it's really important. And that makes sense, right? So a has to be constant. Acceleration has to be constant. So v has to be changing at a constant rate. I know this is, again, more the reality side, more practical side of it. That's not really common, right? In the real world, it's very hard to get true uniform acceleration, but for the problems, they'll tell you. So, and then that's also, again, going back to the average acceleration, instantaneous acceleration, right? If acceleration is constant, right, average acceleration is also constant. So they're all equal. A with the bar is equal to A. So we don't have to worry about any of those like weird definitions or anything. So yeah. Oh yeah, and then for the boxed stuff, I'm pretty sure last time I checked, the boxed ones are the ones that are provided on the table, and here on the right also the reason why you would pick which equation to use. You just take a look at which variable you're not given. Yeah, so I'm pretty sure this one is not on it. So if you want to memorize this equation, basically, big 5 number. I mean, big 5 number 1 is like kind of the basically definition of average velocity. We just moved x over, or yeah, and then big 5 number 4. That's a mouthful. I'm pretty sure it's not on the table of information, but I have to double check. But again, you should be memorizing these equations mainly because they're like they're really important. They come up in and they come up again in 5 rotations. And yeah, these are pretty, I would say, fundamental equations. If you have these memorized, you can really go through these questions like that. So it's much easier to solve. So highly, 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 highly recommend that you memorize these. It's only 4. Yeah, this number 1 you don't memorize. Like that one's the definition of average velocity. But these other 4, the big 4, you should memorize. Okay. All right, let's check them. Oh yeah, I don't want to keep you here forever. So Kinematics Graphs. So those super quickly. So now we're going to move on to graphing because graphs are pretty important. So let's first go through the position time graph. So be very, very, I want to emphasize this so many times, very careful at the labels, your y-axis. So x-axis will always be time when it comes to kinematics, always time. But your y-axis, be very careful. It can either be acceleration time graph, position time graph, and velocity time graph, and all 3 show different things. So here we have position time graph. And you can kind of memorize this, but the slope of your position time graph is always going to be your average velocity. Well, you probably wonder, why is that? The reason, right, we can just go back to definition, right? Average velocity is a change in position or change in over change in time. So, right, if we look at that's literally the definition of, or that's literally what slope is, right? Change in y or change in x. In this case, it's change in position, which is y, and then change in time. Like the change in y over change in x. So that is why the slope of the position time graph is average velocity. So if ever you're given a graph, position time graph, and it says find average velocity, you find a slope. So it's not a trick question or anything. I think I have, what is this? Oh, yeah. So again, going back, really, really important, right? Let me just pull this up for a second. So this is again position time graph, right? Here it's just asking for a velocity. Right, so you just take the slope against all that slope. So in this case, let me go back for a second. So in this one, this is easy because they're all just straight lines. Here, where it's curved, right, you can still find the slope. You just got to find the tangent line at that one point. That's kind of how you find the slope of the point. I wish I find label the magnitude. So don't worry about things. Trying to look for the steepest, because the steepest is going to give us like the most close to vertical, I guess you could say. The biggest drop, that will give us the greatest. So we only throw out magnitude. That is the steepest, what do you call it, tangent line out of the 3, or the 5, I should say. And then which is velocity 0, right? Remember, just the slope. You just draw the tangent lines, right? So it's not asking when position is 0, it's asking when velocity is 0. So you draw your tangent lines. That is when your tangent line is going to be horizontal, because tangent y and tangent x is 0. And that's going to be C and E. So kind of the graphical one. Okay. Oh, and then really quickly, just go back. I completely forgot to include slides on this, but so going off this definition, right? If the slope of a position time graph is average velocity, then the slope of a velocity time graph is going to give average acceleration. Oh, and then we can also, I'm surprised I didn't add these slides in. Maybe that's okay. I'll just say them verbally. And then we can go back to the integral stuff. Remember, so this is calculus kind of a concept, but right, integral is area. So that means, right, if we're given, right, a velocity, what do you call it, a velocity time graph, right, a velocity time graph, and you find the area between the graph and the x-axis, or I should say the t-axis, because it's time. So if you find the area between the graph and the t-axis, you actually get displacement. Remember, so that has to do with the, right, so you go from velocity to displacement, you do integration, I should say. So yeah, that, again, integration area, we're kind of connecting those concepts. So one more time, slope of position time graph is average velocity, slope of velocity time graph is average acceleration, and the area between the velocity time graph and the t-axis is the object displacement. So you can either memorize that, or right, you can just take like what you know and kind of apply the knowledge of derivatives and integrals. Okay, I think that's basically it for graphs. I just realized I want to. Okay.
Sorry about that.
Yeah, go ahead. Yeah, go ahead.
I just thought this was like maybe worth adding, I guess. And I'm not like 100% sure if you did mention this or not. But like if you were asked for like instantaneous velocity, given that like position time graph, you would still like use the slope, like over that little interval, right? Because like any slope at like, excuse me, like the derivative of like a linear graph at like any point in like an interval, I guess, is the same as like any other point, if that makes sense, right?
Yeah.
Okay, right, thank you.
Like the tangent line at one point, that is instantaneous. Yep, you got it. You got it. Okay. Yeah, I know average and instantaneous are always a big topic in physics. Good. Just make sure we clarify. But yeah, the tangent. Yeah. So again, you're given a point, right? If you find the tangent line to that point, that is instantaneous, which is cool. Okay. Oh yeah, this is free fall. Okay, so now we're gonna move on a little bit away from that stuff. We're gonna do a new topic. A lot of 2D kinematics problems like to play around with free fall. Basically, free fall, in its most simplest terms, right? It's just an object or a person or whatever is falling due to gravity, acceleration due to gravity. So I'm gonna be super technical about it. So just some important notes, right? So if we're using the kinematic equations and an object is experiencing free fall, just remember that A is going to be, you basically take the kinematic equations and you replace A with G, because that's the only acceleration it's experiencing. It's from gravity, it's falling in the air. G, just to know, it is a positive constant because it's the magnitude of the acceleration. So I know sometimes if you label down as negative, you would think, oh, yeah, negative 9.81. And that is true. Let me see, hold on, let me just pull this up. Yeah, but right now we just care about, if we're just naming G, we just call it a positive. That's just, it represents the magnitude. G, on the exam, it's actually okay to use 10. I had to look that one up. I used 10 on the exam and I did perfectly fine. I know some teachers are very strict, at least my teacher. I don't know what you guys do. My teacher was very strict about it. For some reason, I don't know, we had to use 9.8. Actually, we had to use 9.81 for all of our problems, and it kind of threw me off. I was like, wait, do we use 10 or 9.81? Yeah, you can use 10. That's fine. Also makes your calculations a little bit easier as well. Let me see if there's anything else. That's basically it. Oh yeah, and the gravitational acceleration vector, right? Vector points down. Yeah, it's pretty, because gravity goes down. Let me see if there's anything else I wanted to mention. I did write down some notes if I wanted to see thing. Oh yeah, so one more thing, direction. So I know this is pretty, it's kind of a confusing topic. So technically, right, G, let me move this up for a second. Yeah, so you want to use the big four, right, equations for any kind of kinematics related. So even for free flow questions, you want to make sure you use those big four. But then there kind of becomes like a problem, like, do I label, is it negative, is it positive, what is A, what is G? So this is where it gets a little confusing. So remember, for direction, if we're being technical about it, you can actually label positive and negative depending on what you want. So I guess most people, we always write down as negative, up as positive, but we always assume that for the most part. I know most people, we just assume, right, up is positive, down is negative, and that's just like the natural thing to do. However, it's important to note that that's not like a set in stone rule. It is possible for you to label down as positive, depending on what kind of problem you're working with. You can label down as positive, like sign-wise. It is okay. So I know sometimes we're a little bit hesitant, like, but that's what we've been doing for so long. We've been setting down as negative, up as positive. But it's important to note that that is not a set in stone rule. You can assign down as positive if that's kind of what your heart desires. Then obviously, certain things like velocity, if that's the sign you've chosen, then that means, right, if velocity is pointing down, it would not be negative, it would be positive, right? Make sure you really, really clearly label your directions, especially for the big four equations. When you plug in things and you don't have the correct negative, positive, answers start getting weird. You might get the wrong answer because you used the wrong sign. So make sure before you start the question, you are super, super clear. You've labeled what is up, what is down, what is positive, and what is negative. I mean, up and down, you can't like choose up is up, down is down. But for sign-wise, you want to make sure, usually the convention is write down as negative, up as positive, but depending on the question, if it's easier for you, you can set down as positive, which is cool. Okay, so let's just keep moving through. Baseball is interesting. All right, and then we're gonna do a quick little 2D motion. We're almost done. We're almost done. 2D motion, projectile motion, right? So in general, right? Any object that kind of like moves, right, in real life, right? If I throw a soccer ball, it's not just gonna go straight down, right? Because of right, launch angle, for example, right? If I launch the soccer ball at an angle, it's not just gonna fall straight down. It's gonna follow like a parabola trajectory kind of thing. So that is, I have a cool image for this. Yeah, here it is. So if you want to memorize this, you don't have to. It just makes your calculations a lot easier. But however, you don't have to memorize this, but you should be very, very, very comfortable with this. So whenever you're working with projectile motion, remember, I'm just gonna move from bottom to top. So from acceleration, right, vertical motion. Oh yeah, one more thing. You have to make sure that when you are doing projectile motion, anything 2D, we always, always, always analyze horizontal and vertical motions separately using the big five equations, right? So we always make sure it's super clear that you label what is the horizontal stuff, what is the vertical stuff. The vertical stuff you put Y's, horizontal stuff you put X's, right? We do it separately, which is very interesting. So always make sure you create some kind of table like this when you're doing these problems so you don't get confused, because it can get kind of confusing. But these are just the things that you should automatically just write down. For projectile motion, your acceleration and x direction is 0. We're not accelerating at all in the x direction. It's just the velocity, and it actually just goes to the next part, right? Your initial velocity in the x direction will always be equal to that. So even if I just pick a random point on that parabola, the velocity in the x direction will be the same as the initial. That's important. Whereas in the y direction, your acceleration in the y direction obviously is, and here they just put negative g. So in this problem, they've labeled basically, what's it called, down as negative. So they've put the negative g. That's usually the convention. Most people, right, you don't think, oh yeah, down positive. Usually, we just do is negative. That's fine. To find your velocity in the y direction, remember, so it's important. It's not constant, not like the x one, because right, because acceleration is acting on it, we know that velocity is changing, right? Just based on the definition, right? Acceleration means velocity is changing, which means it won't be constant. So we have to calculate for that. We use one of the big four equations. We can use this one to kind of find it. Going to position again. obviously position is changing, right? Because it's going from here to here. Position is always changing, so you would use this equation for that, and you can use one of the big four or big five, I guess, big five equations. All right. Ooh, let me go quickly. We're almost done. Oh yes, we did it. Oh my gosh, wait, I still had one more slide. Oh, that was it. That was cool. So that was basically it. That was my brief overview. 24 slides. We did it. Yeah, so that was basically, again, an overview, review. We did a couple of practice problems. I'm thinking the next office hours will probably do an overview of Newton's laws, because I find those to be really, really important. Right, F equals ma. It's like whenever someone thinks of physics, we think of that. That's the first thing that pops up, hopefully. But yeah, that's basically it. I guess if you guys want, I can probably do another. Yeah, this was an overview. This wasn't like a super elaborate. But I think it was a good review for anyone who needed like definitions, for example, all that in the slides. So yeah, that's basically it. So I think if you guys want, I can probably do another office hours, just practice problems, no definitions, no explanations, or yes, explanations. That's the homework first problems, like no like definitions, no mostly just questions and explanations. That's what I'm thinking. Do you guys want that? Like I do have my notes from last year with all my like practice problems and stuff, with the answers and stuff. So we could probably do that, because again, Kinematics there is a lot. Oops. To it. Where is my yes, let's see, are we gonna cover resistive? Oh yeah, resistive forces. That is, oops, I clicked the wrong button. Oh, my computer is like being loud right now. Okay, yeah, resistance forces. That is stuff like air resistance, anything that like resists. We could definitely we'll probably cover that, not in kinematics, because for the most part air resistance doesn't really play a part. However, actually, it might come up in Newton's laws. I'm just checking my notes right now, because I do have them here. Things like errors. You know what? I do remember resistive force. It's definitely in the last unit, after the very last unit, which is gravitation. Resistive force. There isn't a formula and stuff for that. Yeah, resistive force is in the gravitation unit. I do remember that. Stuff like it's like somewhere in the back of my folder, but yeah, resistive force will definitely probably cover this. Oh, dynamics. Oh, that's interesting. Yeah, that's weird. Yeah, I definitely did not learn resistive forces in kinematics. I learned that in gravitation. I'm not sure, but yeah, I guess it depends. But yeah, I mean, it's a type of force. I would assume it'd probably be like one of the early like forces stuff, but yeah, resistive force is not too prevalent. But yeah, awesome. Yeah, thank you for. Oops, hold on. 500 buttons just popped up. Okay. So yeah, thank you for coming. Thank you for watching the replay. If you're watching the replay, I had so much fun. Let me close this. Okay, awesome. So I think I'm gonna end the stream here. Let me stop sharing for a second. Congratulations. Okay, cool. All right, so yeah, if anyone has any questions, you know where to find me. I'm in the Slack channel like almost like every day. I am here to explain it. My specialty would probably be, right, if there's a really hard concept, I can explain it in like basically super simplified terms, because that's kind of how my brain works. I don't like to explain things in like, for example, if I need help, like okay, this is interim, like right, if I need help for something, like I don't want someone to explain it in like super complicated terms. That's like the reason why I don't understand it. Like I would love if someone just explained it in like super simple terms. I will be that person. If you have a question or something, I will explain it in super simple terms to kind of help you understand. So I'm here always for you in the Slack channel if you need any help. Thank you so much for coming. And I think I'm gonna pause. Oops, how do I end the meeting? But yeah, thank you so much for coming. Have an amazing week. Bye. Adios.